Okay, let's continue. Again, for all the lectures, what I'd like for you to do is actually look at the video, review the PowerPoint. There are some class participation Word documents in Blackboard under lectures. Please look at it, try to answer before you see the answer in the PowerPoint, and apply your knowledge this time towards there's going to be a lab. So today we are going to look at SQL. So in the grand schema, we look at the conceptual model, the what, and we use the ERD language. Then we map that to the language of how, which is the internal, and we use the relational model. And today we are going to look at SQL is the implementation language. SQL is a standard to talk to database management systems. SQL stands for Structured Query Languages. And again, if this is the DBMS software, then through it we can create relations or tables. The relational model, the how, is actually very powerful. We can express queries very easily. It's just a two-dimensional data structure. Now, executing the queries is actually optimized inside the DBMS software. And again, we'll go into some of the layers of the customary DBMS system software, and we'll look at that. Operations. If we actually deal with relations, the operations will be maybe select fewer tuples in a relation, maybe project, that means eliminate some of the attributes or fields, and also we can do a join between two tables to answer some of the queries. So again, please look at the class participation, challenge yourself, and let's start with the SQL. That's exciting. SQL was developed by IBM in the 70s. Remember Cod, he's the one that created the relational model. And there are several standards, but vendors actually create their own versions, and they don't necessarily adhere to standards. So when you actually compare the BMSs, there will be minor differences. A database is made of relations, and so if we look at the relation, it's made out of type variable. So one is the schema, specify the name of the relation, the name and type of each column, and also you have an instance. So that type variable, like in our third generation languages, that would be an, let's say, int, and this will be an x. Now, in the SQL, which is a fourth generation language, the instance, the X is actually a set of tuples, so it's pretty heavy duty. Okay, first command, drop table. There are keywords. This is your table. And again, if this table has children, you can execute. These are keywords, cascade constraints. So I'm mentioning here the Oracle built-in data types. So you have char, varchar2, integer, real. Also, there's a date and some other built-in data types. So if this is the student schema, it has 1, 2, 3, 4, 5 attributes. I can actually create table. These are keywords, these students. And again, we do see this format. This was the preferred format to use for the relational model. And the reason I insist on you doing that is because that will actually teach you SQL. So it's not something that is new. Open parenthesis, close parenthesis, you need a semicolon if you want to execute this. So this table has SIDs, 20 characters. You can put primary key on the same line, or you can say primary key in parenthesis SID. Here's the name, login, age, and the GPA. So this is the relation that will be created. SID is the key. And again, if I want to see the description, I can use SQL command describe students, and that will show me the relation or the table. Now what I have done, I actually run this command. So here is the drop table, create table, and describes students. And again, that will be the output. Now, once I have a relation table, I need to insert tuples. So insert into is another SQL command. This is your relation. And these are values. Hopefully the types match the domain type for the when you created the table of students. So how many tuples I'm going to create? 3 of them. So if I actually look at the table or relation, these are the tuples that I have inserted. So cool. So this is shows you an example of a SQL command. So a comment. Okay, another command. I want to delete from keywords students where the name is Smith. As you can see, there are two Smith names. So after I execute this command, what I have in the table is just one tuple. I have deleted two tuples that matched the Smith. Very good. So let's continue. So again, this is the tuple. So I did run these SQL commands. Update. So I want to update students. I want to set the GPA to GPA minus 0.1, where the GPA is greater or equal to 3.3. So I have one tuple here, and this is greater than 3.3. I'm going to subtract 1. And after I execute this SQL command, this is what my table looks like. So I'm running this, and you can see that output says that that is a 3.3. Very good. Querying tables. For example, I'm interested in finding all students in this instance that are 18 years old. And how would I actually, intuitively, I see what the output should be, so I can do it manually. But here is the command that allows me to create that query. First of all, what is produced is an output relation. So you need to figure out how many attributes that output relation has. If it's all the attributes and you don't want to project, then it's pretty straightforward. So the only condition I have to put is where age is 18. What about writing the SQL for it? Again, the keywords for SQL, you have select, from, and where. So select, and again in the select, if I want to actually select all the attributes from the existing table students, I can put an asterisk instead of a comma between the attributes. And this is the where condition, age is 18. And if you actually run this command, you will get output. What if you want to just find the names and the logins, only the name? Then instead of using asterisks, I can say name, comma, login, and I will only have two attributes. So my output relation will only have two attributes. So that's pretty cool. So if this is executing the second query, you can see that. Okay, so creating tables, again, the domain constraint is going to be enforced by the DBMS at the moment you create the table. So you cannot enter an age that's, let's say, a real number. Now, what about foreign key constraints? So I have a table enrolled that actually has the SID is a foreign key pointing to the student. So a student can be enrolled in many courses. So the enrolled, so I'm creating this instance of students and enrolled. So here is my students. It has 3 students. And here is the enrolled, and I inserted 4 tuples into that. So when I, for example, can query multiple tables instead of one, again, select from where, select, I'm interested in only the student name and the CID. And obviously name and CID come from two different tables. One is the students table, the other one is enrolled. So in the from, I can put actually, this will be a relation list. There will be two relations. And here are my conditions. Again, I want the foreign key to match the primary key. And this is the condition. We can see the AND operator. Again, these tuples are sets. And I also want the grade to be an A. So this will return all the student, the name of the student that got an A in what CID, course ID. So the answer is output relation will have two attributes, and the only tuple that qualifies is the name is Smith. And let's see, he got an A in topology 112, 53650. 53650. So here is the answer, which is again in itself a relation. So I did verify this, that is correct. Another SQL command to destroy or change the table is, drop table is to delete it. The second one is alter table. These are keywords. Students, for example, I want to add one more attribute like first year of type integer. So I'm changing the schema of the students relation. Now, let's take now a step back. So this is the ERD. This is an entity set with three attributes. One is underline. To convert to a relation, remember, place the oval, label it, and then if you use the table format for the relational table employees, that's your relation name, and you have SSN name and lot, primary key SSN. If you actually want to create a SQL for it, you just put the create. Everything else will be the same. So you can see the benefits of using for the how the table format for the relations you create. Pretty sweet. Okie doke. What about relationship set to relations? Again, relationship set will connect to one, two, or more entity sets. And the rule are the relation is going to contain its own attribute plus the connecting entity set's keys. Now, each one is going to be a foreign key towards the entity set that is a primary key. So here's my employee. Here's my departments, and this is again the order you have to create, because you need to actually, when you create this third relation based on the relationship set works in, you need these tables so you can actually specify. So let's look at the works in. How many attributes? 3. Very good. And let's look at create table works in. So SSN, DID, and since. These are my 3 attributes. The primary key is the keys of the connecting entity sets, and each one of it is a foreign key. So again, these are keywords. Foreign key references employees. So you have to create employees and departments before that. Pretty straightforward, right? Very nice. Now, I did create those, and so integrity constraints, domain constraints, primary key, foreign key, they come from the domain. So again, we are trying to do analysis of the domain by textual based on the requirements that were given to us in a natural language. And again, based on the customer, client, the users agreeing that these are the domain data and the constraints. So once I create a relation and I specify some constraints, then the DBMS will actually not allow illegal instances. So again, remember the constraints, the data is actually coming from the domain, but if we create a relation based on these constraints, the chances that you'll introduce data entry errors are lower. Let's look at the many-to-one. So I have now the requirement saying each department has at most one. So here is my arrow going towards the E on the one side. So again, I would like for you to use this format. So how many relations? I have the E on the one side, employees, and then the relationship set, and the E on the many side will become another relation. Please use the oval, label it. Don't just throw ovals, then labels. I mean, this is actually, I'll say, 20% of the effort, and again, it is very important. So here's the department manager. Okay, so let's see if I want to create a table for the department manager, which is this relation. Again, SSN, that's the connecting entity set, its own descriptive attribute, and the attributes of the E on the many side. So here's the DID, DNAME budget. Here's the SSN, and here's the since. The primary key is just DID because DID and SSN, it's a super key, is not a primary key. And again, SSN will be a foreign key pointing to the employees, but make sure that employees is created first. Okay, so let's look at the key. So a set of fields is a key for a relation. If not two distinct tuples have the same value in all the key fields, and it's a minimum subset. Okay, so there's not a subset that will also this make two distinct tuple not having the same values. Now, if part 2 is false, that means it's not minimum. That is a super key. Now, sometimes there is more than one key. Again, minimum set of attributes, and they are called candidate keys. And again, the DBA together with the client will determine which one to choose to be the primary key or the key. Again, remember, minimum set of attributes. So if I say SID GPA is a key, SID by itself is a key. So again, this has to be a minimum. So that would be a super key. Referential integrity is when you have two relations that are connected through a foreign key. So I'm using the second format for the how. And again, you can see the student ID is actually a foreign key into the student's relation, and that is the SID. So again, some decisions to be made is actually enforcing the referential integrity. For example, can I add a tuple in enrolled that doesn't have a parent? Can I delete a parent while there are children in enroll? So these are some decisions, and I'll show you the 4 options that typical DBMSs will allow you to use. So here is an instance of the students and enrolled and the courses they are enrolled. And to create the table enrolled, it's SID, CID, and grade. And primary key is SID, CID, and that's a foreign key into this. So this will be the foreign key into the student's relation. So, enforcing referential, what if an enrolled tuple with a non-existing obviously is rejected, right? What if you delete a tuple in students and you have children in enrolled? What are you supposed to do? Either delete the enrolled, that's the cascade, disallow the delete of the parent until you manually delete all his children, then the parent, or maybe you are allowed to create a SID that it's a default SID or a null. But again, I'll say the first and the second option are simpler. Okay, so referential integrity can be specified in these standards, SQL 92 and 98, 99, for deletes and updates. So this is an example. I'm going to create a table enrolled. These are the attributes, and I can say, again, I need a comma right here, on delete cascade. So if I delete the parent, the children will automatically be deleted by the DBMS. On update, I want to set to default. So these are some usages. So these are actually in the standard no action. That is the default. Cascade, delete the children. You can use set null or set default. So this is 1, 2, 3, 4 options that are given to you for referential integrity. Again, the semantics of the real world need to be discovered by the DBA that designs the database. Then through the DBMS, you can actually specify the constraints. Again, how would I know the student ID or PeopleSoft ID is the key? Because I understand the domain. How do I know Social Security is unique? Because it's understood. But other than that, you have to actually work together with the client and understand their domain data constraints. So key, primary key, foreign key are the most common integrity constraints. Okay, what if I have a full participation? So must have, every department must have manager. So again, typically this is double, you have an arrow that sticker, so total participation. Again, we looked at this when we did the how, and the only thing I have to say not null for the SSN. So I'm adding this not null in this example. But again, you have to talk to the client and see what their requirements are, understand them. But this usage on delete, no action, so it's just to show you examples. But this full participation must have, that means you cannot have a tuple in this department manager relation with a null SSN. So that is straightforward. Again, weak entity sets, like in this ERD, you have a department policy, so you have an employee and the dependents, and it was assumed that the dependents are unique by identified by name, but that is weak because you can have more than one with the same name. So again, this is the E on the one side, assume that's done, and this will be the other relation, department policy. How many attributes? I have to pull the SSN from the parent, so 1, 2, 3, 4. But for weak entity sets, the key, primary key will be SSN together with PNAME, and again, SSN has to be a foreign key pointing towards the employee. So let's look at this department policy. So here's PNAME, here's age, here's SSN that I pull from the connecting entity set, here's the descriptive attribute. The only difference, the primary key is SSN together with the PNAME. And again, SSN is a foreign key, and I can specify what I want to do or for many to one. Okay, another ERD is the is. So here are the three entity sets. This is a relationship set. You have to actually understand if you can allow both an employee to be both hourly or contract, any employee to be either hourly or contract. So these are decisions you have to make. But converting this to relations, we did look at the two different approaches. First, I create three relations, 1, 2, 3, but this will actually pull the SSN from the employee. Or I can actually create two relations, and again, I have to repeat all this in the two relations. So these are the choices. Okay, views. Views can be used, and I'll show you the SQL syntax to create views and drop views, but the views are based on your underlining physical tables attributes, and you can pick any from any table. Now, the problem is if you drop the table and you have a view based on it, that will automatically be dropped. So the syntax to create views, create view, straightforward. Please pick a good name. This view will have two attributes. Select is a keyword, so this comes from the student name, this comes from the enroll grade, From I have two relations, students and enrolled, where again you have to match the primary foreign key, and I want the age less than 21. So young active students are the students, the name and the grade, they are less than 21. So this is an example overview. It's just like a relation. It has two attributes. But again, what is stored is the definition, not the tuples, because every time the underlying table tuple instances change, the view is going to change. So this is the view that was created. And the content depends on the underlying table instances. So less than 21. I have, okay, this actually removed the Smith as a duplicate. So I have 18 and 19. Smith got a letter of A, and Jones got a letter of B. So B comes from this table. How do I know? Jones 53666, 53, and you can see the B. Let's look at the Smith. Now I did remove um, less than 21. So the Smith is this Smith 53650. So this is the Smith. Okay, so we are going to use for SQL these three relations with the schema: sailor, sailor ID, sailor name, rating, and age. The boats, boat ID, boat name and color, and reserves, the sailor ID, reserve boat ID on this date. So these are the keys, and these are example instances. So here is an instance for reserves. It has two tuples. Here is an instance for sailors with we did look at SQL. Let's introduce it formally. This is the syntax: select from where. And again, the relation lists are the list of the relations that are actually going to be used. So this is an actual example. There are two relations. That will be your relation list. The target list will be the attributes of your output relation. So again, the SQL takes relations and produces a relation. You name the target list are the list of attributes. Of course, it has to come from the relation list that you have specified. The qualification, like this example right there, will actually eliminate some of the tuples from the two relations. You can use the keyword distinct to remove the duplicates. The default is not eliminate the duplicates. Now, let's see what happens when I actually try to evaluate this. Again, this is a very fourth generation language. There are two for loops that actually will allow you to do that. So in order to answer this query based on the two relations, students and enrolled, first you have to compute the join of the relation list. So this is the join. Then I want to discard the tuples that fail to qualify. I'm applying the sigma or select. And these are examples of formulas or conditions that will disqualify the tuples. Then I want to delete the attributes that are not in the target list. So I'm applying this operator pi. If this thing is specified, then I have to eliminate duplicate rows. And so this is very the least efficient. Because when you actually do a join, let's say if you have a relation 1 that's 1,000 tuples and relation 2 that's 6,000 tuples, you'll end up with the join relation that's 1,000 times 6,000 tuples, and that's a lot. Okay, let's apply our knowledge of SQL. Here's the query. Find the names of the sailors who have reserved boat 103. So manually, if you were to do that, You have to say how many attributes your output relation, because you need that for the select. It's just one. You just want the name. Now, how many relations are involved to answer the from? The boat ID is in the reserves, and you want the name, so the relation list will be two relations, the sailors and the reserves. And the condition, of course, you have to join on SID, and also you have to have the condition that the BID is 103. So doing it by hand, this is the upper relation. It has one attribute, and the only one, so this is both 103, 58, 58, the name is Rusty. Now let's write the SQL for it. So first I'm going to compute the join between the two relations. Let's say the instances for the sailors contains 3 tuples. The instance for the reserve is 2 tuples, and actually I'll end up with 6. So computing the join, this is the 6. So I go in a for loop from each one. I join it with each one on the other one. So here's 22 twice. Then here's my 31 with twice, and 58 twice. Again, this is 3 times 2 will be 6 tuples. Wow. Then I want to apply the selection. So applying the selection, I'm going to eliminate all but one tuple that qualifies. So again, the SIDs match, and the boat IDs 103. And then what I want to do is project. So my output relation will only have one attribute in the target list, S-name, and this is how I come up with the answer. That's pretty convoluted. So again, this is done using 2 for loops. You can imagine if you have 2, 3, 4, 5 relations and you do the join first, it's actually very inefficient. Now, we didn't look at this. These are called range variables. So sailors, a range variable that can be used inside the select statement. Reserves are, it can be used inside the, again, I can actually answer that by using just S-name, sailors, reserves, and say sailors SID. But again, sometimes I have to create more than one instance of the relation to actually answer the query. So please, it's a good style to use these range variables, and I want you always to use them. Okay, let's answer. So I have 2 instances, sailors and reserves. I want to find a sailor ID who has reserved at least one boat. Okay, so the thing is, if you actually do a join, you are only returning the sailors that have a reservation, right? But output, again, the approach. Output relation, how many attributes? 1. So let's answer manual. How many relations? 2 of them, sailors and reserves. The conditions, again, the join on SID, it will actually give you only the sailors that have a reservation. So the output, if you are doing it by hand, so 22, that'll be Dustin and Rusty. Now, okay, so can we add distinct? Does it make sense to add distinct for SIDs? Obviously not, because SID is a key. But what if you actually want distinct for other attributes that are not the keys? Then it makes sense to use the distinct if you wish. Now, let's look at the select statement and the expressions. So here is my select. I can use the keyword like, and this is a regular expression, so it has one character, it starts with a B, one character, 0 or more, and it ends with a B. So this will be at least 3 characters, and it starts and ends with a B. Now, another thing I want to show you is actually you can name your output relation attributes. For example, how many? I want to return 1. My output relation will have 1, 2, and 3. Now, this is calculated, age minus 5. This is Um, Again, S age is not calculated as the actual age. But no, actually it is. So it's 2 times. So if I want to actually give a name to the output relation, I can use either the format age1, that will be my output relation attribute name, equal, or I can use this and use the keyword as. SQL is a very powerful language, but it's very intuitive, so it's easy to write simple queries. So this is how I can actually rename the output relation or result relation fields if these are calculated. So we'll look back. Let's introduce some more power. Union, intersect, except. Again, what I'm dealing with is sets, and these are operations on sets. So more set operations in, um, uh, any, all exists. Or you can actually put a not in front of any of these operators. Okay, let's have some more fun. I want to find the names of the sailors who have reserved a red and a green boat. So again, same process. This is write a program that does this, or write a function that does this. So number one, how many attributes my output relation will have? Answer is 1. Number 2, how many relations in the from do I have? Obviously, the red and green appear in this table, and I am looking to actually join, so the answer is 3. And let's try to do it by hand. So a red, or a green. So 102, 103, 104 are red or green. I'm looking at the reserves, and I see 102 and 103 were reserved. I get the SID, and the name is Dustin. 58, the name is Rusty. So here's my output relation, and let's write the SQL for it. It's pretty straightforward. Select SID from sailors S, boats B, reserves R. Here's my where, and SSIDs are SID, and RBID is BBID, so I have to join on BIDs. And here is my condition. B color, and that's for the boats, is red, or B color is green. And again, I can answer the same thing using the union. So what I can do is select all the reds. So here is the set of reds, and here is the set of greens, and I do a union, I'll get the same answer. Or I can use except, or an and so forth. Like I said, it is a powerful language. What about another one? Find the names of the sailors who have reserved a red and a green boat. So again, the process. Output relation has how many attributes? 1. The from, how many relations are involved? 3. And then the conditions. So again, I need to join on SID. I need to join on BIDs because that is the primary foreign key. And also the condition, I want an and between the red. So let's look at 102 is red and 103 is green. Okay, so do I see a sailor ID that has reserved 102 and 103? Yeah, 22. What about another one? Let's say 103 is a green, 104 is a red. If I look in the reservation, 31 has 103, 104. So SIDs 31, 32. Names are Dustin and Lover. Now let's write the SQL for it. So this is using the AND operator, but please note that I am using 2 instances. That's why I need the range variable. So I have a set for B1 R1 and I have a set for B2 R2. So I have 2 sets of the same relation. And again, this is the condition. B1 color is red and B2 color is green. I can also use the intersect. and this is the intersect. So one set will give me all the reds, another set will give me all the greens, and then I use the intersect operator. Pretty cool. Let's answer another query. Find the names of the sailors who have reserved boat 103. I thought we did this before. But this will be answered using nested queries. So the condition, the where, can be a query by itself. So I want the name and the sailors from sailors. But again, the inner query is going to be done first, and let's look at that. So here's my where. So this will be executed first. So I'm going to select RSID from reserves, where boat ID is 103. Yeah, right here. So I come up with 58. And then I'm going to use 58 in this other table and return the name. So first I'm going to do the inner one, return the SID 58. And then I'm going to execute this query and use 58 and grab the name for it. That's pretty powerful. If I want to answer, find the sailors who have not reserved, I can use instead of N, not N. So the combinations are limitless. Okay, so this is the same thing using the exists. So again, inner query is executed first. So I want to select everything from reserves, where the BID is 103, and also the sailor SID is RID. So what I'm returning is the name if such a tuple exists. So that's pretty powerful, and allows you to actually write a lot of SQL, but none of it is relevant unless you test it. Make sure that it returns the correct tuples. Very nice. Okay, so we just see examples of set operators like in, exist, maybe unique, and again, what about if I want to find a sailor whose rating is greater than that of some sailor called lover? So I need to get lover, find his rating, and then return the sailors that have a rating greater than his. Intuitively is easy to do. So again, let's look at the inner query. And I'm going to select the rating from sailors for lover. And then I'm going to return everything from sailors that have a rating greater than any. So that's op any. Op can be greater, less, equal, greater, equal, less or equal, or not equal. So here's the operation greater than. That is pretty cool, isn't it? Okay, now let's answer this using the intersect and using the in. So, so I want to select the sailor ID from sailor boat reserves, where SID, again, foreign primary key, foreign primary, and B color is red. But again, this is actually asking you to answer the end. Okay, so this is a different way of using an end. So end, so SID in, so you actually compute the set of the greens, and the SID has to be in the green. So this is using the end in operator. So, but again, these are two different sets. You can actually use except or not in. So again, you can see that this is really a very powerful language. What about the names of the sailors who have reserved all boats? Again, same thing. How many attributes? 1. How many relations? 3. And where's the where clause? So first of all, here are all the boat BIDs, 101, 102, 103, 104. You have to look in the reserves for an SID that has all of them. And you can see SID is 22 and the name is Dustin. So I'll put relation 1 attribute And let's write this by using division. Doing it by hand is challenging, but writing the proper SQL is also challenging. So this is a solution to answer that by using what's called the division. We'll look into this some more. So I'm interested in the sailor names from sailors such that there's no boat B, and that's all the boat IDs. There is not. So where does not exist uh, a boat from boats that does not appear in the reserves as a tuple in the reserves. So this is so this is you'll find only the ones that exist in the reserves. That's pretty heavy duty. So what we have done today, we looked at a new model, which is the physical model, and we used this implementation language called SQL. And again, we do see that the relations that we are created using the integrity constraints and how to actually query these relations. SQL is a fourth generation language. It's based on relational algebra. Again, algebra is plus, minus, multiply, divide operators on relations. These are your nouns. And we did use the join, we use the select, and we use the pi, which are the operations. Pi is the division. Uh, and again, it's a very powerful language. We can express lots of queries, and anyhow, you can answer the same thing many ways. But again, have in mind the optimizer changes the evaluation plan. I think it's the worst one is to do a straight join instead of maybe eliminating some of the tuples, so do a select, or even projecting before you do the join. But that's the job of the optimizer because we don't want to wait forever to get these answered correctly. Think of PeopleSoft database that's using Oracle DBMS. And you have millions of students and you are trying to search for something based on maybe two tables and you wait there for minutes. So again, this is one of the advantages. So enjoy it. And again, please look at the video. Please look at the class participation and answer the questions before you look at the PowerPoint animation answers. And also there's an assessment. Please take it and work on the lab.